Welcome to this video. In this video we will see further remaining heat treatment processes. So normalizing. So in normalizing we will heat the steel above upper critical temperature, which is 910 degrees Celsius, approximately 50 degree above upper critical temperature, so about 960 to 970 temperature, and then holding to the temperature for some time. So after heating to 910 temperature, we have to hold it to the temperature for some time, and then we have to cool it in steel air. Means we have to keep it as it is without forcing any air over it, and naturally we have to allow it to cool. So what happens is there is a sufficient time to have some grain refinement, and the internal stresses are reduces. So in annealing we are cooling it extremely slowly inside the furnace, but here we are allowing it to cool it in steel air. So the grain growth is not as much as annealing, but it is still quite better. Now the structure obtained is fine perlite, and we call it as sorbite, and this fine perlite is having extremely high ductility with retained hardness inside it, because in annealing what we do is we have complete ductility. Means there is a complete removal of hardness and brittleness, because the grain sizes are much bigger in that, and here there is a retained hardness inside it, and there is some ductility present. Means there is a quite good amount of ductility present inside the material with the hardness. The next is the quenching. So in quenching the steel is heated again above upper critical temperature and held at that temperature. Similarly as normalizing, we have to heat it above upper critical temperature, and then after this holding of the temperature is because in both the process we have to hold it so that the heat enters till the central line of the material, and thorough material in and out is completely at the same temperature, and there is a grain refinement from inside and outside of the material. We'll discuss based on this concept, we will discuss some interesting phenomena in future videos. And after holding it to that temperature, we have to dip it inside the water, oil or molten salt bath. So here there is a much higher rate of heat transfer coefficient in this, because the fluid has higher heat transfer coefficient as compared to air. So there is a much faster rate at which the material cools, and there is a very less time to grain growth. Means the heat out will be so much high that there will be no grain refinement, and hence very fine grain size are obtained inside the material. So grain size is related to hardness, because the more finer or more smaller the grain size, it will have the obstruction or resistance inside the dislocation motion, because material inside the material, if there are more number of grains, there will be more number of grain boundaries present. So the dislocation or the defects has to move when we apply the load, and if there is a grain boundary, all the dislocation will accumulate at the grain boundary, and there will be a strain hardening phenomena, and also there will be resistance to the dislocation, and resistance to deformation. Resistance to deformation happens because of that. And in water quenching, martensite microstructure is obtained. So we have new microstructure here, martensite, which is extremely hard. Its Rockwell hardness number is 65, and this hardness number is asked in many exam repetitively, so remember this value. And martensite is not present in iron carbon diagram. We have all the other microstructure present inside the iron carbon diagram, but martensite is not present, because the iron carbon diagram we developed by slowly cooling. The temperature we are changing in iron carbon diagram, we are cooling it very slowly, and we are also holding it to the temperature, and then after we take the sample and see the microstructure. And here we see the martensite, we water quench it, or oil or molten salt is there. So the heat out rate will be so fast that we cannot attain it in slow cooling, and we cannot show it in iron carbon diagram, because the martensite is developed by rapid cooling in water. So these are the two heat treatment processes. We will further discuss the remaining processes in future videos. So thank you for watching this video, and see you in the next video.